Okay. All right. So, hi. I sent you an email that I have to cancel my office hours today. I'm sorry about that. You guys saw that, right? But I am around tomorrow. Oh, also, I was going to assign problems from the application section, like I mentioned in class last time. But then I looked at the application section versus the problems from just 1.7, which is about what we were talking about on Tuesday, and I felt like that 1.7 was easier than having to dive into some like weird, ugly applications where you'd have to like the numbers get bad and you have to interpret everything. I was like, as I said, I was going to try to be nice and give you something easier, but like I actually think that just giving you the problems from the next section was easier. Also, I want to give you a midterm. I said something about this the first day of class, that what it's going to be is I'm going to just release it on Gradescope as a timed thing, like a 4-hour. Like I don't want to like schedule an evening exam or something. So it's like a 4-hour release window. Once you start it, you'll have like 4 hours to upload your solutions. And I'm writing the test to take like 90 minutes, but I just want to give you plenty of time to make sure you can like scan and upload and submit. So once you start it, you'll have like, so just pick a time, let's talk about what it is. But then I think what I said, and I'm trying to write some stuff this weekend to more lay this out, is that think of it as a first attempt at the test, and I'll grade it and give you feedback, but then you can rewrite anything that you aren't satisfied with your score on and submit it for points. I mean, I think for full points. Like I want you all to get good grades. I don't really, like I don't know. I almost want to be one of those people who just doesn't give grades, but if you're gonna take the time to like rewrite those nicely and then you'll have mastered everything on the test, then I'm happy to give you a good grade. So that's my attitude about it. And yeah, I mean, if you don't do the rewrites and don't turn it in, you could, but so I may even be a little more harsh than usual on the first round just to make you really rewrite stuff nicely on the second round. But then, so the timing of this now is what I was thinking. So I want to do it just instead of a problem set time period. We usually have like Tuesday to Friday, Friday to Tuesday. So I wanted to just do it instead of one of those. We could do Tuesday to, you probably want a weekend. Would you like a weekend? See, I'm gonna screw over Kevin here in both of my classes. It's gonna be the same time frame as our other exam. Then we can always talk and make arrangements. But I think I want to post it next Friday, and then you'll have until the following Tuesday with the grace period even to Thursday. Like the same thing. Like if you just need to find a time to do it. And you can make a cheat sheet, like a note sheet. I'll post about all this, but maybe if I give it to you, I post it next Friday, do the following week. Because that's still the week before spring break. I think we have 3 weeks after this week until spring break. So if I post it next Friday, do the following week, then I can give you feedback by the week before spring break, and then we can do rewrites and stuff. We can either do rewrites before spring break or right after spring break, depending on how. Yeah. Is it okay? First, you just said okay. I said, is that okay? And you just looked away from me.
Oh, I mean, I'm going to be away all weekend.
Okay. But, yeah, you can use the grace period until Thursday. So everyone else think that's okay? Okay. So yeah, I'll post more about it over the weekend. I have a major deadline of my own. I'm trying to get done by 5 o'clock today. So, but yeah, I will have a lot more time after today, which will be nice. Okay, so yeah, back to math. So if you go to the handouts page, we've really covered most of these first 3 handouts. And we sort of put a lot of things together last time about connecting linear independence and pivots and homogeneous solutions. And on the other hand, connecting span and general solutions to systems and pivots, pivot rows and pivot columns. We wrote all this stuff down kind of carefully. And so we really have so far these 3 we have three perspectives, kind of. We have this row perspective of like treating the rows of a matrix as, you know, coefficients of a system of linear equations. We have this column perspective of like treating each column as a vector and looking at linear combinations of vectors. And we kind of have like the echelon form pivot perspective of like, once we've reduced something to echelon form, we can usually make conclusions about it. And I think I mentioned on the homework, even due for Friday, or maybe that you can use row reduction calculators now. Like row reducing by hand is kind of annoying and tedious. Of course, the ones that have letters in them, which I like to assign, you still probably have to do those by hand because you can't type letters into the online row reduction calculators, I don't think, like variables. So you may have to do some stuff by hand, but I try to pick ones that weren't too horrible. It's more just like, it's more like make a couple row reduction steps and then be able to make the proper conclusions. But now I want to introduce a completely new perspective. This is our last major perspective, really. But we're going to also have all these equivalences between all the different perspectives. And like one of the things we'll do is there's a whole handout on there about like conceptual equivalences, like translating from one perspective to another. That's kind of one of the big parts of this course, is like looking at matrices from all these different angles, being able to say things in different languages and see what's equivalent to what. And then there's this whole thing called the invertible matrix theorem we're going to state, which has like k parts, and it's like all these things that are equivalent. K is what, 12, 11? K is the 11th letter of the alphabet, so 11-part theorem. Actually, I think they add more later in the book to where it gets up to like p parts, which is 16. I'm trying to find out 16 part. So like we're gonna be able to say all these things are equivalent to each other. Okay, so this is this new perspective, the linear transformation perspective. And we'll talk, I'm gonna talk a little bit about this, and then really we're just gonna do group work just to get used to this stuff. But it's a new way to interpret, you know, like we can write down a linear system and just interpret it a slightly different way. And here I say, like, let's actually think of the numbers after the equal signs as variables. We've been doing that a little bit, writing like B1, B2, B3. Let's actually call them Y1 and Y2 now. And we can really think of like X as inputs and then Y's as outputs. And so really it's like you can think of a matrix as defining a function. If you think about your math, I mean, one kind of general thing I wanted to say is if you think about your mathematical history and progression, let me write some of this on the board. If you think about your progression through mathematics, right? Think about like functions, right? We start with just y equals f of x. That's one input, one output. And really all through high school, pre-calc, all that stuff, single variable calculus, that's all you're really thinking about, is having one input, giving one output, right? But then you go to multi, and all of a sudden you can have two inputs and one output, or three inputs and one output, right? So that's like, then you look at things like z equals f of x comma y, and w equals f of x comma y comma z, and that's like multiple inputs, one output. You even look at vector fields in multivariable calculus or in physics or something, where like you're at a point, like think about gravitation, right? You're at a point in space, and there's actually an arrow sticking out of that point. So like you're at a 3D point, and you get a 3D, and for every 3D point that you can think of as an input, wherever you go, there's a 3D arrow, which is your gravity arrow. You know, obviously all of our gravity arrows are the same here, like the same acceleration. But you know, if you're somewhere in space, right, your gravity arrows could be different, or it could be zero. So that's actually an example, like vector fields are an example where you can have multiple inputs and multiple outputs. But here also is an example, like multiple inputs, multiple outputs. So like ax equals y. And this is a fairly simple version of this because it's linear. It's just linear combinations of the input variables. Like there's no x squareds, there's no x1 squareds or sine of x1 or anything like that. So really we're dealing with like a simple thing where sort of we could say, for example, if A is a 2 by 2 matrix, like on the screen in the handout, then the input x is in, I've been using this symbol, right? In R2, like it lives in the plane, like it's a vector in two-dimensional space. And the output, so you can think of that as two inputs, two outputs if you want, or we can package it together into a vector. Right, we could have thought of these as functions of vectors if we wanted to. We didn't really do that in multi, but we could think of the inputs as a vector if we wanted to. Or more generally, if A is an m by n matrix, because that's our kind of generic matrix, m by n, m rows, n columns, then I think x, the input x, right, we said that lives in n-dimensional space, and the output y lives in m-dimensional space, because it's a linear combination of the columns of A. And the columns of A have m entries, right? So that's an m. Okay, so now like that's kind of, and honestly, that's what we do in math is, in fact, one of the themes in math reasoning I talk about is that everything is a set or a map between sets. And map is just a word for function. And as you go in math, as you go farther in math, you can just start to write everything down as sets and maps. And so our sets here are n-dimensional real space. And our maps are going to be like basically given by a matrix, right? And this transforms you from like n-dimensional space to m-dimensional space. We're actually going to see actually all sorts of interesting geometric transformations, like rotations of the plane and stuff, can be realized as by matrices, because you can think of inputting a two-dimensional vector and outputting the two-dimensional vector that's like rotated 90 degrees. So there's inputs and outputs there, and it's maps. So yeah, so function slash, we'll use the word map. And then here, this is called this, we can really think of this as a function, a map, or the word we're really going to use for it is a linear transformation. And the way we're going to write it, sorry, I should have just written all this up here, is, here we have like a function, like, we have a letter for our function. We can do the same thing here. We usually use capital T for transformation. But now this really is like a function input. We're supposed to think of it that way. And then the output is y. So I'm still using x and y for inputs and outputs. Yeah, exactly. Yeah.
I don't see why x would live in Rn dimensional space instead of Rn. So like if you made like, let's say,
well, here's a 2 by 3 matrix. Yeah, but but think about if this would be like coefficients of variables x1, x2, and x3. So there's 3 variables, right? So, and it's like 2 equations. So the output is, yeah, that's always the thing that you have to get used to with these, is like, it's like, it looks weird. Matrix multiplication never looks quite right. It feels like it would look right if this was the same height as this, right? Yeah, good. That's good that you asked. Yeah, so it really is, yeah, the number of columns matches the number of variables, which is really in terms of system of linear equations, which is the number of inputs. And then, yeah, thinking of this, I mean, I remember that this is the same dimension as the number of rows, because it's like, we can think of this also as like x1 times 1,4 plus x2 times 2, 5 plus x3 times 3, 6. So that means that the output is just a linear combination of the columns. Right. Good. But yeah, we're gonna write this. And even, I think I even say some stuff lower down on page 1 of the handout. That we even write like, the real way mathematicians write functions is they think of the like input set here and the output set here. Sorry, let me share screen. They think of this like, we'll often write things like this, like the input sets are in, the output sets are in. So like the arrows suggest that like you're putting stuff in here and getting stuff out here. You know, so like this notation, and I'll give you some of these terminology also. It's not super duper important. It's more important in math reasoning and beyond, but figure I might as well give you some of the terminology now that like we actually write, we write something like function colon input set, which has its own name, the domain, output set, which has its own name, the codomain. It's a little different from range. So for example, like if y equals f of x equals x squared, right? Then we could just write f, and the inputs are real numbers and the outputs are real numbers, right? Or if we had, where is this now? So if we had, you know, z equals f of x y equals x squared plus y squared, then let me use a different letter, g. Then we could have g, the inputs are 2-dimensional and the outputs are 1-dimensional, right? So we can write stuff like that. I mean, you could, and like what we do in math reasoning is we start looking at really abstract things like the input could be the set of all cars and the output could be the year it was manufactured. So that would be a function from the set of cars to the set of years. You know, like you can do really abstract things, and that's what you do in higher math is you start inputting. You can input, I mean, you can think of the derivative as a map. It's a map where you input a function. It's like, so you can have some set of all functions on the real number line, and the output's another function. So the derivative itself becomes like a map from one function space to another function space, or the same function space. So there's like all sorts of weird, you know, you can take this really far, which is why mathematicians like to do this now. So, and so, right, so here if we had, right, that t of x equals ax equals whatever I just wrote, 1, 2, 3, 4, 5, 6 times x1, x2, x3 equals y1, y2, which is y, then we would write t as a map from R3 to R2, right? 3-dimensional space to 2-dimensional space. So those are just some examples. Okay. And like I said, there's a bunch of terminology here. Yeah, like I said, the words that used are function or map or transformation, and in linear algebra, we really call these linear transformations. So that's going to be the important. I mean, I think the title of this handout was like matrices as linear transformations. And then, yeah. And then, like I said, there's the input, you probably heard the word domain for the input sets, right? Like if you want to think about the domain of like the square root function, you can't input negative numbers. The domain is non-negative real numbers. Range and codomain are slightly different, right? Like the squaring function I say is a map where you input reals and output reals. And that's before you, if you think about just like I don't know, philosophers would say like a priori, before you analyze this map at all. It's just a map that you inputs reals and output reals. But then when you think about it, what kind of reals does it output? Could I get -3 over here as an output? No, right? It only outputs real numbers greater than or equal to 0. So the codomain is R, but the image, the range is R is non-negative real numbers. So the range is different from the codomain. But we're gonna, and then there's this word image that's used for range. And we'll talk about that because that's gonna come up here. I mean, again, I'm just sort of previewing stuff and we're gonna do a bunch of examples and work through it. But one of the things we're gonna try to figure out is, does the transformation actually, you know, hit everything in the codomain space, in the output space? Like I can imagine a map from R3 to R2 that sends X, Y, Z to just the x-axis, x comma 0. So in that case, the output would be one-dimensional. Even though the codomain is R2, the output would just be the x-axis. So we're gonna talk about stuff like that, right? So that's just, I'm just kind of just giving you a sense. Oh, you know, I have so few examples in my head that I just said out loud. This exact one. Let me share again. Right, this is my go-to example, clearly. The domain and codomain are both real numbers, but the range is real numbers greater than or equal to 0. Okay. And then in linear algebra, we call it the image. Actually, in most parts of math, the range is called the image. Because we want to sound fancier. Okay. Yeah, so really, what I was thinking was just to have you guys get into groups and sort of go through some of these examples, just to get used to how these things work. So like we'll start with an example, you know, 2 inputs, 2 outputs. Here's an example, 2 inputs, 3 outputs. Here's an example, 3 inputs, 2 outputs. And then some nonlinear transformations, and there's some more generous stuff. Yeah, if you want to graph these things, I mean, that's the other issue that we have. Like, we're able to graph functions of 1 variable or functions of 2 variable because we just need 2 or 3 dimensions. But now if you have an input of 2 dimensions and an output of 2 dimensions, the graph would really be in 4 dimensions. So instead, what you end up doing is something like here, where you draw the input and then you draw the output, and then you just draw some examples and like see what they end up doing over here. So there's some problems like that. I don't know if we'll get that far today, but yeah, so we can really just work. This is a long handout, so. So should we do group work? Yeah, I'm excited. I can tell you're excited. Hey, I already lectured. My whole earlier class was a lecture, so I've been lecturing for like 2 hours now. So group work would be good for everyone. So can we do the same groups? Do you want to switch it up, or is the groups fine? I guess there's like a social pressure to just say the groups are fine. So, okay, at some point I'll switch the groups up just to make it more interesting. But today, you can find the same groups that you were with. If your group members are not here, you could try to combine or join a different group or something. But yeah, and I'll pause the recording. All right. So, yeah. So, okay, so you guys, right. So I just wanted you to get some used to some of this stuff. There's some interesting things going on here. One of the things the whole thing with like B and C and E all being connected, is that when you're letting y1 and y2 be variables, right, let me just write this down. So we had this transformation, and it was 5x1 plus 3x2, 3x1 plus 2x2, right? And that equals y1, y2. But we can also write this as the matrix 5, 3, 3, 2 times x1, x2 equals y1, y2. Or we can write this as sort of an, or we can just sort of write the augmented matrix. And then you sort of suppressed the x variables, right? And asking about the image is asking like which possible y1 and y2s can you plug in here and actually get x1, x2s that map to those related. If you plug the x1, x2 and you get the desired y1, y2, right? And I guess I was giving an example over there. Let's just do versus T1 of x1, x2, which is, if I did 6, 4, 3, 2 instead. So 6x1 plus 4x2, 3x1 plus 2x2, and that's y1, y2. Then we could write that as 6, 3, 4, 2 times x1, x2 equals y1, y2, or the augmented matrix again, right? We could write it as that, or we could just write it augmented matrix. And here, if you row reduce it, you get this, right? Because the 6 is twice 3 and 4 is twice 2, then this would row reduce to something like, that was y2 minus half of y1. Is a way to do that. And so what we can say is that y1, y2 here is in the image of T1. If and only if y2 minus 1/2 y1 equals 0, right? And that's a line. So the image here is a line. Equals line. Versus here, this row reduces to, actually you guys did it later, right? You guys did it later. 0, 1, 1, 0, 0, 1. And then what are the formulas you had? Like 2y1 minus 3y2 minus 3y1 plus 5y2. And so now this means y1, y2 is always in the image. We can always solve for x1, x2, right? So it's really, again, we can translate this to different languages. We could say the system's always consistent, no matter what the choice of y1, y2, right? Whereas here, the system's not always consistent, depending on the choice of y1 and y2. Always in the image. So the image equals R2. But it connects back to questions, right? We ask about whether systems are consistent. This is consistent for any choice of the numbers after the equal sign. This is only consistent for certain choices of the numbers after the equal sign. But we can also give the column perspective. I could even written this a fourth way, actually, if I think about it, right? We could also have written this as x1 times 5, 3 plus x2 times the vector 3, 2 equals the vector y1, y2. So an equivalent question we're asking is y1, y2 a linear combination of 5, 3, and 3, 2? And the same thing I could do here. And basically the answers are always yes, like this is always consistent, the systems are always consistent, this is always a linear combination of these two vectors, this is always in the image. It's the same question, just 3 different ways of saying it. If that makes sense. I'll try to write some of this down more carefully, like next week when we have more time, but I just want to point out that you kind of all the same questions related to each other, which is sort of interesting. The other thing I just want to say is that there's this thing where T of 1, 0 perfectly gives you the 5, 3, which is the first column. T of 0, 1 perfectly gives you the 3, 2, which is the second column. So in fact, it's almost like all you need to know is where I goes and where J goes, and that kind of tells you everything. We'll talk about that more later. And then the other big thing that we saw today was the pattern here, right? The pattern right here. Sorry, let me just see where I'm gonna put this. So we had this matrix, we could say this is A, right? A is 5, 3, 3, 2. We also have a matrix coming from this. And that's the matrix 2, -3, -3, 5. And a lot of you were noticing how similar these looked. And also, this is what you do to undo the transformation T, like to go backwards, right? Like, because now if I plug in x1, x2, I get this y1, y2. But now if I plug in this y1, y2, I get back x1, x2. It turns out that this is called the inverse matrix. We're gonna, again, we'll talk about this a lot more. I'm just teasing stuff, but this is called the inverse matrix. And for 2 by 2, there's actually a nice formula for an inverse matrix. It does involve the determinant, though. Do you know the determinant of a 2 by 2 matrix? Have we talked about that in this class yet? It's basically the AD minus BC thing. What is the AD minus BC here? If I multiply this diagonal and subtract, it's 1. So it turns out you have a 1 over the determinant in the formula. Because the determinant was 1, I picked these numbers specifically this way so that you would get nice numbers here. Otherwise, you end up getting fractions, and it becomes a little less obvious. But it turns out the way to invert a 2 by 2 matrix is swap these two numbers on the main diagonal, make these two numbers negative, and write 1 over the determinant in front. And that actually works. And you can show that in general. It's kind of nice. So it's like a first example of that. But again, we'll see it a lot more. Okay, so I just want to get used to some of this terminology and stuff. And it's kind of fun. So this one would not be invertible, right? We couldn't, because we can't solve for y1 and y2 in terms of x1 and x2. And in fact, what's the determinant of this? 6 times 2 minus 4 times 3? 0, and you can't divide by 0. And that's 1 over, I said 1 over the determinants in the equation. So that's like not an accident. So it's kind of neat. There's like all this cool stuff that we're going to see, but we're not quite there yet. We're getting there. All right, thanks guys. We'll call it a day there. Like I said, I'll post more about the test over the weekend, and I'll post homework for Tuesday. And you guys are good.